concept of population in statistics is the population of an infinite number of values. But there is sort of an equivalence in reality of that. For example, if we are interested in the height of all Australian people, well, all Australian people is not an infinite number of people, but it's a very large number of people. So we have an equivalence, the population of people with a population and infinite number of values. But when we talk about sampling distributions, there is absolutely no equivalence of this sampling distribution to something in reality. Therefore, we need the service of our friend, the probability demon, to do these sampling distributions, because it's an absolute abstraction that doesn't have a match to reality. Okay, so we are going to use as an example Galton's data that we mentioned before. It contains data on the height of parents and offspring. In this case, we are going to take into account that we've got only the information of the population of parents, of the heights of parents, and the information we have is that the mean height in that population is 68.308 inches. This is the original data set, so we use the original measurement scale. And the standard deviation of that population is 1.787. So here we have, this is a population of heights of people in England in the 19th century. It's not an infinite number of values, but it's a very large population. But for the purposes of the statistical modeling, we are considering this as the population. So and we describe that, we specify that as a normal distribution. For the analysis that we are going to do, this is not necessary. It doesn't need to be a normal distribution, but it could be a normal distribution. So this is the information we have. We've got a population with a mean and a standard deviation. Now we want to investigate whether we are going to collect data in offspring. We're going to measure the height, and we want to see whether the height of offspring is the same of that of their parents. Now, we need to establish a null hypothesis, as we discussed before, and the null hypothesis more technically would be that the random sample of heights of offspring that we plan to measure comes from a population of heights with the same mean as that of the height of parents. So we are saying that the sample of values of heights that we're going to measure comes from the same population, or a population with the same characteristics as that of the population of heights of parents. So that's the null hypothesis. The null hypothesis typically is that we are not going to find differences in something, or that what we are going to collect in our sample is the same as some predetermined value. A typical null hypothesis is a value of 0, but it doesn't need to be like this. So in this case, we can define a null hypothesis in a different way, which is the same as this one. For example, we can say that the difference between the mean of the sample and the mean of the population is 0. That's another way of expressing a null hypothesis. Now, remember that Fisher indicated that that's the hypothesis that we are going to test, the null hypothesis. But we are interested in the alternative hypothesis. The reason that Fisher says we need to test the null and not the alternative is because the alternative hypotheses we can propose are not exact. So here we got 3 possible alternative hypotheses. The first one is that the random sample of heights of offspring comes from a population of heights with a different mean than that of the heights of parents. So we are saying that, unlike the null hypothesis that says that there is no difference, here we say that it is different. But we are not saying whether it is higher or lower. In the alternative hypothesis 2, we are saying that it's higher, so we give it the directionality to the hypothesis. And in alternative hypothesis 3, we are saying that it's lower. And depending on the hypothesis that we are interested in, then the analysis that we're going to do differs. In this case, I'm going to use alternative hypothesis 1 only, which is that the heights come from the mean, the height, the values of height in the sample of offspring comes from a different population than that of parents. Okay, so let's go through the procedure we have to follow if we follow the method that Fisher proposed as to test a null hypothesis. So the first is to develop a test of significance. So here is the test of significance and the procedure. So the first part would be to plan a number of measurements of heights in offspring and calculation of the mean of that sample of heights. So that would be the task, the tool that we are going to use to measure. The second step is to find out the sampling distribution of the mean of heights from a population in which the null hypothesis is true. So this second step is equivalent to, in the lady T case, it was when we consider the possibility of the possible classifications that someone without any knowledge, without even tasting the tea, would do. So someone that shows no effect. So in this case is the same. We are assuming the null hypothesis is true, and we need to find the sampling distribution. I haven't explained what the sampling distribution is, but we are going to do that soon. The third step is what Fisher said. We need to decide, before we run the experiment, which values we are going to consider significant and which values are going to be considered not significant. So in this case, we are going to decide which values of the mean of the sample will be significant and which not. And this is to determine an alpha level or a level of significance or a significance threshold. The fourth step is to conduct the measurement of heights and calculate the mean of heights in offspring. The fifth step is to determine the probability of obtaining the mean observed or a more extreme value in offspring in that distribution, in the sampling distribution. And this is the p-value. The last step is that if that p-value is lower than the alpha level, we decide to reject the null hypothesis. Otherwise, we maintain the null hypothesis. Okay, let's go step by step. Step 1. We need to plan a number of measurements of heights in offspring, and the calculation of the mean of that sample of heights. So what we are going to do is to collect data in 928 offspring. This is what Carlton did. So we are using his data in order to exemplify this procedure. Second step, find out the sampling distribution of the mean of heights from a population in which the null hypothesis is true. Okay, this is the sampling distribution, and as I mentioned at the beginning, we need the services of the probability daemon. Okay, how do we calculate or generate a sampling distribution of any statistic? In this case, we're going to use the mean as the statistic of interest. So remember that this is absolutely hypothetical. No researcher would actually do this. This is something that the computers do that for us. So first of all, we need to remember what would be a population in which the null hypothesis is true. Okay, a population in which the null hypothesis is true has to have the same mean as the population of parents. So the mean is 68.308. And we are going to assume as well that that population has the same standard deviation as the one of parents, which is 1.787. Now, the next step is for the probability daemon to obtain a random sample from the population of the same size of that of the planned sample size in the study. So, in our study, we are going to obtain a random sample of 928 values. So the probability daemon will do the same as what we did. It will obtain from the population of values, a random sample of 928 values. Next step, it will calculate the mean of this sample of 928 values. These are 928 heights, and we can easily calculate the mean of that sample. Now, we've got one sample and one mean, but we keep the mean only, and we don't care about the sample. So this process is repeated thousands of times. Let's say 10,000 times. Now, what we have is 10,000 means. And with these 10,000 means, then we create a distribution of means, which is the distribution of means under the null hypothesis. That is the sampling distribution of the mean. So let's see some characteristics of that distribution. So we started with a population in which the mean was 68.308 and the standard deviation was 1.787. Now, the sampling distribution of the mean will have the mean exactly the same mean as that of the population. And then that sampling distribution of the mean has a standard deviation. And the standard deviation is called the standard error. So why do we call standard error to the standard deviation? Well, standard error is the standard deviation of a sampling distribution. So in this case, the standard error, we say SEM, so SE for standard error, the M is for mean. So in this case, the statistic that we are doing a sampling distribution of is the mean. But in other cases, we have other statistics. So it would be then the standard error of the other statistic. Now, the standard error of the mean statisticians have worked out over the centuries what a shortcut in order to obtain that. So we actually don't need to do the sampling distribution. If we have this shortcut, that's it. That's what we need. And that shortcut, it is that the standard error of the mean, of the standard of the sampling distribution of the mean, is calculated as follows. The standard deviation of the population, which we know is 1.787, divided by the square root of n. And n is the sample size of the sample size of the sample we obtained, which was 928. So that value is 1.787 divided by the square root of 928 is 0.059. So you can see that it's a very, very small standard deviation, and you can see how narrow this standard distribution is. So if you compare with the distribution of the population I showed before, the x-axis has exactly the same values and the same distance, so it was a much, much wider distribution, and this one is a very narrow distribution. The next step is to decide which values of the mean of the sample will be significant and which not, or in other words, to define the alpha level or the significance threshold or the significance level. So Fisher recommended, but just by passing, say, well, 0.05 or 5% seems like an adequate level of probability to determine whether a result is significant or not. And that comment was taken on face value, and that's what, since he made that comment, researchers that adopted Fisher's method have been using that level for many, many decades, when it was just a suggestion, not a postulate or a decision made based on any justification. Okay, but let's follow that advice, and we establish an alpha level of 0.05. What does this mean? Well, it means that we want to only determine that a result will be significant if the probability of obtaining the mean that we obtain in our sample within that distribution, this sampling distribution of the mean, is lower than 0.05 or 5%. And because what we want to do is if we reject the null hypothesis, so if we reject the possibility that the sample we obtained comes from the same population, then that the height of parents, we don't want to make that rejection and make a mistake. So we try to reduce as much as possible, but we need to have a threshold that we are comfortable with, and that threshold is here 5%. So one way of doing that is to determine in this distribution what two values or an interval of values contain 95% of the probability distribution. And we need to take this 95% should be central. So everything that is beyond the upper boundary of this interval or below the lower boundary of this interval, then if the mean in our sample is anywhere there, then we are going to reject the null hypothesis. But if it is within that interval, we are not going to reject the null hypothesis. So we worked out that the values in this distribution that contain 95% of the probability of the whole distribution are 68.19 as the lower bound and 68.42 as the upper bound. So when we collect the data, if the mean of offspring comes below 68.19 or above 68.42, then we are going to say that the result is significant. But if it is within these two numbers, then I'm going to say that the result is not significant, and we are not going to reject the null hypothesis. Okay, so next step is conduct the measurement and calculate the mean of heights in offspring. And we've got that data was calculated by Galton. So the n is the number of observations, which is 928. The mean of that sample is 68.089, and the standard deviation is 2.518. So the fifth step is to determine the probability of obtaining the mean observed or a more extreme value in offspring in that distribution. And that's what we call the p-value. It is a famous value in statistics. Every paper that does in psychology that does hypothesis testing, it will use a p-value. Okay, so that value is actually on the left of the lower bound. So remember that the lower bound was in that distribution was 68.19. So we obtain 68.09, which is close to that value, but it's actually outside the interval. So because it is outside the interval, we are going to say that the result was significant. Now, in terms of what's the probability of obtaining that result in this distribution, well, that probability is less than 0.01. So basically what we are saying is that the probability that the value we obtain, 68.09, comes from a population in which the mean is the same as the mean in parents is very low. So the probability that comes from the same population is very low. And because it is very low, we reject that hypothesis. And actually, I anticipated the last step, which is if that p-value is lower than the alpha level, so the p-value was 0.01, and the alpha level, it was lower than 0.01, and the alpha level was 0.05, so it is lower, then we reject the null hypothesis. Otherwise, we maintain it. So we reject the null hypothesis. And it is very important that this procedure, it only allows us to reject or not reject the null hypothesis. Now, obviously, when we reject the null hypothesis, then the alternative hypothesis receives support. But it is not proven. We cannot prove the alternative hypothesis because this procedure is about the null hypothesis only, and we can reject it. But also, if the result we obtain is not significant, we cannot say that we accept the null hypothesis. We say that we retain it, that we maintain it, or that we do not reject it. But we cannot say that we accept it or that we prove the null hypothesis. This method is about rejection of the null hypothesis. So we either reject it or not, but we never prove the null hypothesis and we never prove the alternative hypothesis.